So the first one here, log base 4 of x equals 5. What that is saying is 4 to the power of 5 equals x. What does x have to be? (1024). Very good. 4 to the power of 5 is 1024. Number 2, log base x of 625 equals 4. That is saying x to the power of 4 equals 625. What does x have to be there? It is 5. You would solve that one by doing, of course, a fourth root. Number 3, log base 12 of 1728 equals x. That's saying 12 to the power of x equals 1728. What does x have to equal? Three is correct. 12 to the power of 3 is 1728. So every logarithmic equation can be rewritten as an exponential equation. And of course, the other way around. The next thing I want to do is I want to review our rules for combining and expanding exponentials. So the logarithms, I should say. The one I want you to combine first is 4 log x minus 3 log 2 plus 2 log y. Combine that. And then on the other side, I'm going to want you to expand or break apart the log of 5, actually let's do 25 x to the third over y. I'll give you a couple minutes to work on those. So for the first one, combine. First thing I'm going to do is with each of them is I'm going to combine the number in front with the log. 4 times the log of x is equivalent to the log of x to the fourth. Minus 3 times log of 2 is equivalent to the log of 2 to the third. Plus 2 times log of y is equivalent of log y squared. We know 2 to the third is just 8, so that's really log 8. Log of x to the fourth minus log of 8 is x to the fourth, log of x to the fourth divided by 8. Plus the y squared means we're adding or multiplying the y squared. So that's log of x to the fourth times y squared divided by 8. So that can all be combined into that single log. Any questions there? So then the second one is asking us to go the other direction. 25 times x to the third divided by y. So that's log of 25 plus, because it was times x to the third, log of x to the third, divided by y, so minus log of y. (25) I'm going to write as 5 squared. So log of 25 is equivalent to 2 times log of 5 plus log of x to the third is 3 times log of x minus just log of y. Now this can give us some interesting ways to combine logs. If I have 7 log x plus 5 log x, because this is the same log with the same object, remember when there's no base written in the log, it's assumed to be a base 10, and the object there is x for both logs, we can add them just like we would, 7y plus 5y, or 7/3 plus 5/3. We can combine the counts. 7 plus 5 makes 12, and treat the log x as a name. And we can do the same if those logs are numbers. This might be log of 2, 3 times log of 2 plus 9 times log of 2. Well, again, 3 plus 9, that's 12, log of 2. Well, looking at this one at first glance, log 2 and log 8 have different objects. Can't combine them, right? However, 8 can be written as 2 to the power of 3. So the 5 log 2 isn't going to change, but this is going to be 2 times 3 log 2, because you take the 3 out front and you're left with the log 2. So 2 times 3 log 2 is just 6 log of 2. And now you can combine that. 5 plus 6 is 11 times the log of 2. So we graphed our exponentials. Let's graph our logarithms. If I want to graph y equals log of x, remember this is assumed that's a log base 10 of x. In our exponential, in our standard exponential, y could never be less than 0. Well, remember, an exponential and a logarithm are inverses. That means in this logarithm, x cannot be less than 0. It must be greater than 0. It actually can't even equal 0. So I can only put in positive values for x. Let's go 0, 1, 5, 10, and 20. So we've got 0, 1, 5, 10, 15, and 20. And let's see, log of, well, it can't be 0. X can't be 0, so that was a bad call. Log of 0, if we tried it, is going to give us an error. Log of 1. What do you get when you try to do log of 1?
0.
Is 0. So you get the point 1, 0, which is right there. Log of 5. You get 0.699, don't you? So log of 5 is 0.699. So I'm going to put 1, 2, 3, 4 here. So that's 5, comma, 0.699. Somewhere around there. What's log of 10 if you punch it in? 1. So that gives us the 0.101. Somewhere around there. How about log of 20? 1.301. So it's 20, comma 1.301. Somewhere around there. Well, we need to know what's happening in here. So let's put in 0.5. If I do 0.5 here for x, I actually get a negative 0.301 when I do the log, don't I? So we got 1, 2, 3, negative 0.301. 0.5 is somewhere in here. If I tried, well, let's do 0.25, I get negative 0.602. What we find is this graph looks something like this. Remember on our exponential curve that came in, it was close to 0, it came up, it hit 1 here, and then it curved up quickly. Well, this is doing the opposite. It's coming up here close to 0, hits 1, and then it curves off to the right quickly instead of curving up quickly. Remember, those are inverses. So what y normally would do is now being done by x. So today, our main purpose today is to look at some calculating with our calculator approximate values of logarithms. To do that, we're going to focus in on our standard log, which of course is log base 10. As we mentioned, anytime you see log written with no base on it, we assume it is log base 10. If you have your calculators handy, try to put in the log of 40. You get 1.602? Yep. Perfect. Anybody that's not able to get that to work out? Okay. So now there are some certain numbers. Before you punch them in the calculator, I want you to try to figure out what this should be. What do you think the log of 10 would be? Yeah, it's 10 to what power equals 10? Well, that would be 1. How about log of 1/10? Go ahead and punch it in if you want to. What do you get? Did you get negative 1? How about log of 10 to the 5th? It's going to be 5, exactly. Log of the 4th root of 10. So it might be a little tricky to punch in. Oops. Log of the 4th root of 10, we get 0.25 or 1/4. Now there's a pattern here that you may have gathered from yesterday. We actually pointed out some of these, but not all of them. Log base A of A, log base A of A always equals 1. log base A of 1 always equals 0. That's not an example that we did. Log base A of the reciprocal of A is always going to be what? -1. Kind of a, well, let's do this. Log base A of A to the power of B is always going to be B. Just like log base 10 of 10 to the 5th, the log base 10 and the 10 cancel out, it's just 5. Now I can combine these last two, by the way. Log base A of 1 over A to the B is going to be negative B. Because log base A of A to the B is just B, log base A of a reciprocal is negative. And then the last one down here, log base A of the B root of A is always going to be what? One over B. And those are pretty standard common roots that we run into. Log base 100 of 10 can be thought of log base 100 of the square root of 100. Where did the square root of 100 come from? Why is that going to be equivalent? Because the square root of 100 is equal to 10. Remember, square root of 100 is a root with an index of 2, even though we don't write it in. So that ends up being 1/2. What would log base 1,000 of 10 be? The third root of 1,000 equals 10. So the log base 1,000 of 10 is 1/3. Okay, let's get back to log base 10 and doing some examples with that. On your calculator, find log base 10 of 50. What'd you get? 1.699 is perfect. Log base 10 of 2,000. What do we get? 3.301. Log base 10 of 2. Careful. I believe negative, oops, sorry, You are correct. It is 0.301. Sorry. Log base 10 of 80. $1.903. Log base 10 of 0.1. What'd you get? That's 10 to the power of negative 1. Log base 10 of 0.04. Was that negative 1.398? Perfect. Any questions on those? We mentioned yesterday that natural constant, E, and it comes up all the time in exponential relationships, logarithm relationships, any sort of growth and decay, it's prevalent. Electronics, it's a big deal. It's E is equal to 2.7183 approximately. It keeps on going forever. Because it's such a prominent factor in growth and decay problems, log base E is a common log to use. And rather than having to say log base E, we use the abbreviation ln. It is called the natural log. The reason it's called the natural log is because it is the log of the natural constant. So your calculator has that ln button. Works just like the regular log button. So we can find approximate numbers for ln of 5. Give us 1.609. Find ln of 10. 2.303. Yes. Now notice when we were doing a log base 10, when we doubled the number, it always went up by the same amount. It went up by 0.301. The same relationship exists here. ln of 20 is now going to be what? 2.996. And what you notice is each time it goes up by about 0.693, 0.694 is the increase when you double with the natural log. Note that is different than log base 10. When you change the base of the log, you change what that doubling factor is. For natural logs, it's 0.693, 0.694. What's ln of 1? 0, good. The log of, no matter what the base is, the log of 1 is always 0. How about ln of 0.3? Negative 1.204. Good. Remember, the log, no matter what the base is of some number b, if b equals 1, the log of b equals, oops, put b equals 0. If b equals 1, the log of b equals 0. If b is greater than 1, the log of b is positive. If b is between 0 and 1, the log of b is negative. What if b is less than 0? Let's use ln here again since we'll be consistent. What's ln of negative 2? It'll give you an error. Can't do it. Can't take the log of anything smaller. We can't take the log of 0 or anything smaller than it. On your calculator, you will notice on the log key, there's a second function above it that's 10 to the x. At least on most calculators, that's how it's set up. On the ln key, the second function above it is e to the x. So if you do second log key 3, what that's really entering into your calculator is 10 to the power of 3. Of course, that better be 1,000. If we try it second, oops, clear out. Second log 3, and notice it does even displays the 10 to the power of 3 and gives us 1,000. If we do second ln, let's do 5, that's saying e to the power of 5 is. Give us 148.413. So to find the value of e using this, we would express e as just e to the power of 1. So that means you're going to do second ln 1, and that gives you the value of e, 2.7183. So can you find ln of e to the 8th? Should just be 8. How about ln of the third root of e? Gotta be careful how you enter that one. ln, then you've got to do 3 third root e to the 1, then you got to arrow out to get your parentheses in the right spot. It's 0.33333, or 1/3. Remember, this is log base e of the third root of e. The third root of e is really e to the power of 1/3. So the log base e and the e to the power of cancel out. Ln of the third root of e is just the index of that root as a power, or 1/3. How about ln of 1 over e? What do we get? -1 is correct. So we can calculate those standard ones when they're, the object of our log is expressed in terms of our base of the log. If it's a log base e, as long as e is in our object, we can express them pretty exactly. But what if that's not the case? What if we have, log base 4 of 16? We can adjust that. We can write that as log base 4, and we can write 16 as 4 squared. So of course, what is that going to be? The log base 4 and the 4 to the power of cancel out, leaving you with 2. If I have log base 5 of 625, I can write that as log base 5 of 5 to what power is 625? Five to the power 4, right? So log base 5 of 625 is log base 5 of 5 to the 4th, which is just 4. What if it's not 625? What if it's log base 5 of 600? 600 cannot be written as a power of 5. How can we possibly calculate that? Well, because they couldn't pre-program all of the different bases of logs into your calculators, although I just read something that there is a new calculator coming out that is going to, just like you can put in different indices in your roots, your radicals, there is a calculator that's supposed to be coming out this summer that does allow you to put different bases in your logs. But anyway, for right now, we only have base 10 and base e, log and ln. So how can we calculate a log base 5 or some base that's not either 10 or e? We use the change of base formula. Log base a of b is equivalent to log of b divided by the log of a. So let's use that to calculate log base 5 of 600. That'd be log of 600 divided by log of 5. So log 600 Make sure you use your parentheses to close the parentheses on that root. Divided by log of 5. We get 3.975 to 3 decimal places. Now I get asked every now and then, does it matter whether I use the log key or the ln key? Would that work? Would log ln of 600 divided by ln of 5 work? Of course it does. It doesn't matter which log you use. This change of base formula converts any log into any other log you're able to calculate. So it doesn't matter whether you use log base 10, log base e. You could use log base 2 if you wanted to, if you had that button on your calculator. It doesn't matter. So how about log base 3 of 50? Do that on your calculators for me quickly. So that's log of 50 divided by log of 3. Yes, 3.561. Any questions? Want to do a little bit of problem solving here quick. Solving equations. Log of, let's do this, log of 5x equals 3. If I want to solve that equation, remember we converted it into an exponential form. That exponential form was, there's no base written, so we assume that's base 10. 10 to the power of 3 equals 5x. And then we can solve that. What is 10 to the power of 3? 1,000. So 1,000 equals 5x, and what do we do to solve that? Divide by 5 to get 200 equals x. Now it's not going to be quite as neat but what if I tell you that the ln of 4x equals 8? What is the exponential equation that goes with that? Well, what's the base of our log here? E, right? So it's e to the power of 8 equals 4x. So to solve that, we would do e to the power of 8 and then, of course, divide by 4. So we're back to our calculator. How do we enter e to the 8th and then divided by 4? Well, it's second ln 8. Then we have to get arrow to get out of that power. Divided by 4. So x is 745.24. $239 if you wanted to, if you preferred. So I want you to try to come up with a solution for ln of x over 3 equals 5. See what you come up with there. So this is saying e to the power of 5 equals x over 3. To solve for x, we would multiply by 3, right? So it's 3 times second ln 5. 445.239. Any questions? Okay. A little bit more calculator work for you. I'm going to give you several examples here. I want you to find log base 2 is 17, log base 5 of 100, log base 11 of 40. Now let's do those three first. I'll give you a minute or so. So the first one here is log of 17 divided by the log of 2. Doesn't matter whether you use log or ln. We get 4.087. The second one here, log base 5 of 100. That's log of 100 over log of 5. .861. And finally, the last one, log base 11 of 40. Log of 40 over log of 11. Giving us 1.538. Any questions on those? So now, the big kahuna. What's all this about? Well, inverses. Why are inverses important? Well, we used inverses, we showed, for undoing what another operation has done. And the main place that we want to do that is in solving equations. if I have an equation like x plus 7 equals 18, I solve it by subtracting 7. It was built by taking x and adding 7. I solve it by subtracting 7. If I have an equation like x minus 3 equals 5, it was built by subtracting 3. I solve it by doing the inverse, adding 3. X equals 8. If I have an equation like 5x equals 45, this was built by multiplying x by 5. I solve it by doing the inverse, dividing by 5. X equals 9. If I have x divided by 4 equals 2, that was built by dividing x by 4. I solve it by doing the inverse, multiplying by 4. X equals 8. When I had x to the power of 5 equals 32, that was built by taking x to the power of 5. What's the inverse of that? The fifth root. So I undo that by taking the fifth root, giving me x is the fifth root of 32 is 2. If I had the third root of x is 5, that was built by taking the third root of x. What's the inverse of the third root? Power of 3. So the third root and the power of 3 cancel out. X equals 5 to the third power is 125. If I have 10 to the power of x equals 500, this equation was built by taking x as the power of 10. The inverse of that is the log base 10. Of course, just the log. So now that log base 10 and the 10 to the power of cancel out. I have x equals the log of 500. And of course, our calculator will tell us the log of 500 is 2.699. Or we might have log base, whatever I want to put in here. Let's do log base 4 of x equals 3. This equation was built by taking the log base 4 of x. The inverse is by taking 4 to that power. 4 to the power of log base 4 of x. The 4 to the power of and the log base 4 cancel out. We have x equals 4 to the third power. So x equals 64. So it's just another pair of inverses that we can use for solving equations. We had all sorts of exponential equations we talked about in the last week. Probably the simplest one is a half-life. The half-life, remember, the amount of material left, I'll do m for the amount of material, is equal to an initial amount times 1/2 to the power of t in years, or whatever time the half-life is in, divided by the half-life. So if I had a problem, I could ask, as we did the other day, how much of a 2,000 kilogram sample with a half-life of 17 years will be left after 50 years. See if you can remember how to punch that in your calculator and come up with a result for that. I can tell you this is going to be just over 250, because this is just less than 3 half-lives, and 3 half-lives is 1/8. Let's take a look and see. What's that? 260.404 sounds correct to me. Let's double check you. So 2,000 times, I put my 1/2 in parentheses just to be safe, to the power of, and now I'm going to put my exponent in parentheses since I have to do a division there. 50 divided by 17, close my parentheses. And it's absolutely correct, 260.404. However, we might be asked, how many years would it take for a sample of 800 kilograms with half-life of 6 years to decay to 100 kilograms. In this problem, we not only know the starting amount, that's the 800, we also know the final amount, the 100. So 100 equals 800 times 1/2 to the power of, it's now the time that we don't know. So it's t over 6. Order of operations still applies here, and when we're solving these, we have to do that reverse order of operations. It was built using the order of operations. We take it apart going backwards, going in reverse. So here, 1/2 first would have been taken to the power of t over 6. Then it would have been multiplied by 800. When we take it apart, the first thing we have to do is divide by the 800. We have to get the exponential by itself. Just like in our radical equations, we had to get the radical by itself, we have to get the exponential by itself. The exponential here is the 1/2 to the power of t over 6. So we get rid of that 800 by dividing it out. 1 divided by 800 is 0.125. Now that the exponential is by itself, we eliminate the base of the exponent. The variable is in the power, so we have to eliminate the base. The base here is 1/2. How do we eliminate a base of 1/2 in our exponent? We use a logarithm with a base of 1/2. So on the right side, the log base 1/2 cancels out the 1/2 as the base of our exponent. That leaves us with just t over 6. On the left side, we have to do log base 1/2 of 0.125. That's where that change of base formula comes in. That's log of 0.125 over log of 1/2, or 0.5. Giving us 3. 3 equals t over 6. Now what do we have to do? Times 6. T equals 18. It'll take 18 years for that to decay down to just 100 kilograms of material. Do you guys want to try one? Okay, that was a rhetorical question. How long will it take for a 1,200 gram sample with a half-life of 118 days to decay to 300 grams? I'll give you a couple minutes to try that. So if you write out our formula, 300 is the final amount, equals our initial amount of 1,200 times 1/2 to the power of t over 118. What's our first step? Divide by 1,200. So we've got 0.25 equals 1/2 to the power of t over 118. Now what? Log of 1/2. Very good. So on the right side, what do we have? T over 118. On the left side, that's log of 0.25 divided by log of 0.5, which is should get 2. Correct? Then what do we do? multiply by 118. Of course, that was days, so that's 236 days is the time it would take. So another application we looked at for these exponential equations was compound interest. Compounded annually, the amount that you would have at a rate of R after a certain number, after T years, you would have a F is usually used to stand for future amount or future value. P is the principal or present amount, present value, times 1 plus R, our rate, to the power of T, where T is the number of years. So if $5,000 is invested at 8% for 12 years, how much will you have? So using that formula, we're finding that future amount. The principal is $5,000 times 1 plus, remember, 8% goes in as a rate. That's 0.08, close parentheses, to the power of 12. Giving us 12,590.85. So it more than doubles in that time. It goes up to $12,590.85. Well, let's go the other direction. How long would it take for $2,000 to grow to $10,000 at 6%? Now in this one, we know the future amount. The future amount we want is $10,000. The present amount is $2,000 times 1 plus our rate is still 0.06. We don't know T. That's what we're solving for, T or X, whatever you want to call it. Now the first thing I should probably do here is combine in here 1 plus 0.06 is 1.06. Because I have to have that. It's part of my exponential. I have to have it as a single number before I can do anything with it. Next, I have to get my exponential by itself. I have to isolate the exponential. How do I do that? Divide by 2,000. So 5 equals, the 2,000 is gone over there, 1.06 to the power of T. Give myself a little room here. Now what do I have to do to get rid of the exponential? It's a log, but log with what base? The base of my exponential is 1.06. To cancel that out, the base of my log also has to be 1.06. So that gives me just t on that right side. On the left side, how do I calculate log base 1.06 of 5? That's log of 5 divided by log of 1.06. Which gives you what?
27.62.
You got her. 27.62 years. Now in compound interest, the examples we've done the last few classes have all been compounded annually, so only compounded once a year. That's not terribly practical. On Monday, we're going to look at more applications of these exponentials and logarithms, solving equations with exponentials or logarithms in them, and we'll maybe explore, if there's time, we'll explore a little bit more on compound interest where it's compounded monthly or quarterly. So at this point, we've done all the week 5 topics. So homework 15, A, B, and C have to be done for Monday. Also, by the end of the day Monday, quiz 15 needs to be completed. Remember now, make sure if you have some time, try to get some time to look at that final exam study sheet. Because next Tuesday, we are scheduled just as a review day for the final exam. And what I will do for that review day is I will answer questions off that study sheet. So that's going to be a double bonus for you. It helps you to review for the exam, but also remember, if you complete that final exam study sheet and turn it in, you get extra credit. So if there's questions on there that you're stumped on as you're trying to do it for extra credit, this is your chance to get some freebies. Okay, any questions? You guys have a great weekend. We'll see you on Monday.